So hopefully you've gone through and you're able to define the terms and understand what the terms are from before. In particular, null, alternative, left tail, right tail, two-tailed test, as well as the significance or alpha level and the p-value. If you don't understand those, go back, reread the definitions, and if you need some further help, make sure you email me so I can help you. What we're going to be looking at for the remainder of section 14 is we're going to be looking at a hypothesis test of one proportion. Some ideas of a one proportion test. Remember, we had the claim that 6% of all people have O negative blood. Or we've also used this statistic in class that 11% of people are left-handed. Okay. Another statistic that we might utilize is that 52% of the world's population is female. And so therein lies the question, can we test these claims? So that's what a one proportion hypothesis does. It has a claim made about a population as a percentage, and we're going to go ahead and test that by collecting data. Now, in the past few examples, we only used 100 samples. That was just out of convenience. So let me show you the steps, and then we're going to work through an example problem of this. So the first step is to always define the null and the alternative hypothesis. The good news is that the null hypothesis is always going to be P is equal to mu sub P. Right? In English, what this means is that the sample proportion is equal to the population proportion. Right? So if I took a sample of 100 people, I would expect that 6% of those people have O negative blood. I wouldn't have any reason to doubt that. Or 11% of those people are left-handed, or 52 out of those 100 people are female. However, there might be an alternative hypothesis, and this is what's stated in the problem. All right? There's three possible alternative hypotheses. The sample proportion could be less than the given population proportion. The sample proportion could be greater than the population proportion, or the sample proportion could be not equal to the population proportion. If you pick the first one, that's a left tail test. I'm just going to define that as left tail test LTT. If for some reason in the problem it says greater than, that would be a right tail test. And then finally, if P is not equal to mu sub P, you would have a two-tailed test. It's up to us to be able to define what type of test that we're looking for in the problem. The second step to being able to do one of these types of hypothesis tests is we're going to collect some variables. And I'm going to define the variables for you. There's going to be 5 that you need to collect every single time you do one of these types of tests. The first one that you're going to collect is mu sub P. Mu sub P is going to be the population proportion. 6% of all people have O negative blood. 11% of all people are left-handed. 52% of all people are female. That's something that's given to us. P is going to be the sample proportion. So remember, we had 4 out of 100 people had O negative blood, or 2 out of 100 people had O negative blood. We're going to get that from the problem. Q, as always, is 1 minus P, the probability of failure. N is going to be the sample size. And again, that's given to us. And then the last variable that we need is the significance level. That's going to be given to us in the problem as well. Right. After we do this, then we're going to set up the distribution based on the alternative hypothesis test. So we're going to draw the graph. So it's either a left tail test. And remember, for a left tail test, we just shade in a little bit of the left tail. All right. The range of values is going to be from 0 to 1. And for a left tail test, the cutoff point is going to be alpha. So alpha is going to go exactly where the cutoff point between the reject and the fail to reject region are. This is if, for the alternative hypothesis, we have P is less than mu sub P. Now, if it's a greater than type of problem, that's when we draw a right-tailed test. The range of values on the distribution is still 0 to 1. The only difference is the exact cutoff point is going to be 1 minus alpha. Okay, so this line right here, that's going to be 1 minus alpha, the complement. Similar to a right-tailed test or a greater than problem. This is going to be if the alternative hypothesis is P greater than mu sub P. Right? And then the other option is if for some reason it doesn't suggest less than or greater than, the only suggestion is not equal to for a two-tailed test. So if we have a two-tailed test, this is what it's going to look like. So we're going to have our distribution. The range of values is still 0 to 1. If it's a two-tailed test, we have two tails obviously. And the cutoff regions are going to be half of alpha, because remember with a two-tailed test we have to split alpha in half, and then 1 minus alpha over 2, or 1 minus half of alpha. Just as a reminder, the unshaded regions for all three of these graphs are the fail to reject regions. The shaded region is the reject region. So this is our FTR, FTR, FTR. The other one's the reject. Again, the only reason we would ever draw a two-tailed test is if the alternative hypothesis is when P is not equal to mu sub P. All right, so if I'm numbering my steps, the first step is to get the null and the alternative hypothesis. The second step is to gather the variables. The third step would be to draw one of the three graphs that we have here. We're not going to draw all four of them, or three of them, excuse me, but we're just going to draw the one that's based on the alternative. So we look at the alternative test, and that's going to tell us if we have a left tail, a right tail, or a two-tailed test. All right. Once we know the type of test, then we're going to be able to do some computations. And the fourth step is to get the p-value. The p-value is actually pretty easy to compute. We're going to do it in two steps. First thing we're going to do is we're going to compute this animal called sigma sub p. That's going to be equal to p times q divided by n. And then once we get that, then we compute a z-score. Z is going to be equal to p minus mu sub p divided by sigma sub p. We're going to get an approximation for that, and then we're going to convert that into a p-value using the z-table. Okay? Because remember, a p-value really is just probability. So what we're going to be doing is we're going to be computing the probability and then going through our z-table and then converting. The last step is to derive a conclusion. And there's only one of two conclusions. You can either reject the null hypothesis. And here's how you know what to do. Okay, so if you're going to plot the p-value, and if the p-value falls in the fail to reject region, what that means is that you are going to fail to reject the null hypothesis. In other words, you can't get rid of it. The p-value usually indicates that there's not enough evidence for the probability to be a result of random occurrence. Now, if for some reason the p-value falls in the reject, then what that means is that you're going to have to reject the null hypothesis, meaning that there is enough evidence to suggest that the disparity between the test value and the population value and the test value are going to be significantly different. There's enough evidence in the gap there. Okay. All right. So before we work through an example, I would suggest go back, make sure that you're okay with the 5 steps, derive the null and the alternative, gather some variables, draw a distribution, compute the p-value, and then come up with a conclusion. Once you're okay with that, then move on to the next video where we're going to go ahead and try to work through an example.